Okay, let's tackle this capacitor problem. For the circuit below, V equals 9 volts, C2 equals 3 microfarads, and C4 equals 4 microfarads, and all capacitors are initially uncharged. Switch S is closed, a total charge of 12 microcoulombs passes through point A, and a total charge of 8 microcoulombs passes through point B. What are C1 and C3? So what this problem is saying is that as soon as switch S is closed, charge moves to the right here. 12 microcoulombs passes through point A. 8 of that microcoulombs passes through point B. That means this capacitor has Q4 charge on it is equal to 8 microcoulombs. And 12 microcoulombs had passed through A, that means Q3, the charge on C3, must be equal to 4 microcoulombs. So let's just recall some of the things about capacitors that we know of that we'll be using. First, the main equation is the capacitor equation, and that's going to be given by C equals Q over V. Change in potential across the capacitor, and Q is the charge on the capacitor. So for each capacitor, you'll have a potential drop, potential difference of V corresponding to the capacitor. So C1 would have a Q1 over V1, C2 will be equal to Q2 over V2, and so on. Next rule to know about capacitors is how to combine them. Right now, C3 and C4 are in parallel, and the rule for capacitors in parallel is when you combine capacitors in parallel, they just add. So C3,4, which is the combined capacitance of C3 and C4, is going to be C3 plus C4. Now, what does that C3,4 mean? It means if you replace these two capacitors with just one and call it C3,4, its value would be C3 plus C4, and it would behave no different than when you had two of them separately. So these are again capacitors in parallel, and we can say this is the rule for when you have capacitors in parallel. The capacitances just add. The other thing, what does parallel mean? It means they see the same voltage difference. So this C4 has the same voltage difference as C3. Okay. Another way to think of capacitors in parallel is that I can go through C3 without having to go through C4. I can go this way, or I can go through C4 without having to go through C3. So the phrase that you should remember is same voltage, different charge. So the voltages across C3 and C4 are the same. That means V3 equals V4, but Q3 is not equal to Q4 if C3 and C4 are not equal. So we can find the voltage V4 because we have 8 microcoulombs for charge here, and we know that C4 equals 4 microfarads. So right away we can rearrange the capacitor equation to set this equal to C4 times V4, right? Which means V4 is equal to Q4 over C4, 8 microcoulombs over 4 microfarads, which is 2 volts. So this also means, since V3 equals V4, this also means that V3 equals 2 volts. Okay? And using the capacitor equation for C3, V3 will equal Q3 over C3, which, remember, we're trying to find C3, so we can solve for C3, and that'll be Q3 over V3, which is 4 microcoulombs over 2 volts. And you'll get 2 microfarads. So that'll be the answer for part B. Now, I want to really mention that the key to doing these problems is the notation. Notice that I keep everything separate. Everything has a subscript. So if this is C4, it has a voltage V4 and a charge Q4. And same thing for 3. I always write the subscript so that it can get confusing. So this way it won't get confusing when you try to manipulate all these equations. Okay, so what's C3 for? We just found C3, and that's 2 microfarads. And C4 is 4 microfarads. So that means that C34 is going to be 6 microfarads. Okay, so now we can tackle what is C1. And to do that, it's good to see that C1 and C2 are not in parallel, but in series. And the two of them are also, if we replace this with C34, then the two of them are actually in series with the C34 as well. So you'll have 3 of them, 3 capacitors in series. Now, it's always a good idea to redraw the circuit so that it can be clear what's going on. So if I redraw the circuit, I will have V here, and then let's draw the switch in because it's closed, C1, and then C2, and then we're replacing 3 and 4 by 1 equivalent capacitor, and that's being called C34, right, which we already determined as being 6 microfarads. The C1 is what we're trying to find. C2 is equal to 3 microfarads. The other thing we know is Q34. Remember, 12 microcoulombs had passed through A here. That means 12 of them had deposited itself onto Q3 capacitor C34. So this equals 12 microcoulombs. The last bit of information we know is, since C3 and C4 are in parallel, they have the same voltage. Remember the phrase same voltage, different charge? Well, they would also have the same voltage as the equivalent capacitor, C34. So voltage across the C3, C4, and C34 are the same, and we had found that to be 2 volts. Where we're at now, we have all this information about C34. We have this about C2, and C1 is what we're trying to find. And there's a battery of 9 volts. So at this point, you can treat this as a brand new problem. I'm trying to find what C1 is. These capacitors are in series. So we know something about capacitors in series. First, the capacitances, equivalent capacitances, combine, but not easily like before, where you just add them. it actually looks like this. So if I wanted to combine 1 and 2, I would write the reciprocal 1 over C12. It would be equal to 1 over C1 plus 1 over C2. So in this case, you add the reciprocals. Then take the reciprocal. Okay, along with this, there's going to be a phrase as well. So capacitors in series, you should remember the phrase different voltage, same charge. So remember, for capacitors in parallel, you had the same voltage because they see the same voltage difference. Here, capacitors in series do not see the same voltage because there's a voltage drop here, and then another voltage drop here, and then another voltage drop here. Together, you add all those voltage drops, and it should equal 9 volts. But the charge, though, the charge will be the same. So we know right away that Q1 must be the same as the charge on C2 and must be the same as the charge on the equivalent capacitor C34. And we had found this above. Q34 equals 12 microcoulombs. Okay, so capacitors in series have the same charge but different voltage. The voltage drops, of course, have to, in this case, like we said before, V1, the voltage drop across C1, plus the voltage drop across C2, plus the voltage drop across C34 must equal the total drop, which will be 9 volts. So that's an equation we have as well. Now we already know what V34 is. It's 2 volts. So we can subtract that out. Get V1 plus V2 equals 7 volts. Using the capacitor equation, V2 is equal to Q2 over C2, and these are known as well. So remember, Q2 is equal to Q34. So that's 12 microcoulombs. C2 was given as a given in the problem. It was 3 microfarads. So we can put 3 microfarads here. And don't worry about the units. They'll just cancel out. You don't have to convert to 10 to the minus 6. The microns will cancel out. And 12 divided by 3 is going to give you 4 volts. So we know what that is. We can subtract it out so that in the end, V1 is 7 volts minus 4 volts, which is going to give you 3 volts. And now we're very close to our answer. Using the capacitor equation again, this will be equal to Q1 over C1, which is what we're trying to find. So C1 equals Q1 over V1, or remember Q1 also equals Q2, so it's 12 microcoulombs over the voltage is 3 volts. And so the final answer will be 12 divided by 3, which is going to be 4 microfarads. That for C1. So that's how you do these problems. Remember, we use 3 different things. First, if capacitors are in series, you would add them, right? And how do you know if they're in series? Well, one thing is if they see different voltages. The other thing is they have the same charge. This is a phrase, different voltage, same charge. Another way to think of that is if I wanted to get to C2, I have to go through C1. If the other way, I can't go through to C1 without going through C2. For capacitors in parallel, however, I do have a choice. Here, if I want to go through C3, I can just go through without having to go through C4. So these guys are in parallel. They see the same voltage, and they'll have different charges. And the equivalent capacitance just add, whereas in series, their reciprocals added. Okay, so then you've now finished the problem.